Aby Philip will present about quantum steering algorithm for estimating fidelity of separability. Please go ahead.
Hi everyone, my name is Aby. This is joint work with Surya Ratnasamy, Vincent Russo, and Mark M. Wilde. You can find our archive at that number. Yeah, so first I'll start with telling you about Schrodinger steering. Then I'll tell you about separability and entanglement, the link between separability and steering. I'll explain my test for separability, and then variational, then what I call a variational quantum steering algorithm, then some plots and some computational complexity. So first, there are, if two parties C and D share, distant parties C and D share a pure state, say psi, and then the reduced state is rho. And so then by performing a measurement on D, we can realize a probabilistic ensemble of, with probabilities P of Z and the state psi of Z on C, such that the reduced state is just the sum of these, the product of the probabilities and the states and the sum of the lot. And so this is what is steering. So depending on the measurement, the states and the probabilities will change, but the overall total state will not. So that's what steering is about. And so for a bipartite state, if it's separable, it can be written as a convex combination of pure states that are product over C and D as in equation 1. And any state that is not separable is entangled. And in general, checking whether a state is separable or not is known to be a computationally hard problem, and hence a broad interest in talking about this problem. And so a purification of a separable state can be written like this. Purifications are not unique. All purifications are related by unitary on the reference system. So we add a reference system R to psi to sigma AB to purify it, so that the total state psi RAB is pure. And so the purifications are not unique, and they're all related by unitary on the R system. And so if sigma AB is a separable state, then we can steer the purification into a probabilistic ensemble of product states using a projective measurement on the reference system. So if you change the measurement on the reference system, then the probabilistic mixture that the systems A and B are directed to are different. And so there will be a measurement in which, if you apply that measurement, then the probabilistic ensemble will be an ensemble of product states. So we can then use this. So in general, we have to start, for a general state, we can start with the purification and then perform a measurement on R, say X, and then we can, on receiving X, we'll need to we'll need to check whether the pure state that has resulted is a product state. Now that's where our first test of separability comes in. It's a separability test for pure states, because psi X of AB is a pure state, and we need to know whether it's separable. And for pure state, separability is just checking whether it's product. And so we consider the distributed quantum computation, where there is a computationally unbounded quantum server. I'm sorry?
Please continue.
Okay, thank you. there's a computationally unbounded quantum server called a prover and a computationally limited quantum client called a verifier. So you can think of the verifier as yourself and the prover as some unknown thing that can do all sorts of quantum computation. This is just we will substitute the prover with something more practical, but in a minute. So for a pure state, so psi AB is the pure state that the verifier possesses, and then the prover sends in phi, and then the verifier does a swap test between what the prover sent and one half of their state of interest, and one half of their state. A quantum server is just a quantum computer that we have. That's it. Yeah, it's just a different name. And so, like I was saying, so the verifier is in possession of the state of interest, psi AB. The prover sends along a state phi of A prime, and then the verifier performs a swap test, and once the swap test is performed, the verifier accepts only if the all zeros outcome is obtained. And so now we can check what the maximum acceptance probability is. So this first line of this equation is the acceptance probability. So this is psi AB is our state of interest, phi A prime is what the prover sent in, and what we're doing is projection onto the symmetric subspace. And so the maximum is a maximization over all the states that that are available, and here we can think of that the prover already knows somehow, not too worried about how. And so when we go through the calculation, this 1 plus the infinity norm of partial, the reduced state of A, of psi AB, which is psi A, it's an infinity norm. And so 1 plus psi A, the infinity norm of psi A. And so as you can see, if this state were not if the state of interest is not a product pure state, then the infinity norm will not be 1, and the maximum acceptance probability will not be 1. But if it is product, then the infinity norm will be 1, and then the maximum acceptance probability will be 1. So then prover can always accept. The verifier will always accept, or at least has a high probability. And so now we have a test to show we have a test for the separability of pure states. Now we want to generalize this to mixed states, and so for that we look at this graph. As you can see at this circuit diagram, so this circuit diagram, you can see there are 3 sections. I'll go through all 3 of them. So the first is state preparation, which is you need to be given a purification of your state of interest. So your state of interest is rho AB, and you need to be given a purification of it, which is psi of RAB, suppose, and there is a circuit that realizes this state. And so what we do is then the prover, which is within the dotted box, everything that the prover does is within the dotted box, and the prover measures the reference system, and depending on the outcome, sends back a state to the verifier to perform the product test. So when the prover does a certain measurement, the the prover has then steered the other two systems, which is A and B, to an ensemble of pure states, and then the verifier is left with some pure state, and depending on the outcome X, and so then the prover sends in another pure state to check to do the product test that we mentioned before. So as you can see, epsilon R from R to A prime is an entanglement breaking channel, which is just a measure and prepare. So the mu X R on rho on whatever the system R is, that this trace portion is the measurement, and the psi XA is psi X of A is the preparation part. Yeah, and so our full test will look something like this. So the verifier uses a unitary circuit to produce the state psi RAB, which is a purification of rho AB. Then the prover applies an entanglement breaking channel on R and sends the resulting quantum state to the verifier. The final state is sent to the verifier, who performs the swap test, and the verifier accepts only when the all zero outcome is obtained. So as you will see, the criterion for accepting in both cases is exactly the same, and we can now discuss what the maximum acceptance probability is. Maximum acceptance probability is given like this. So which is so you take your which is the trace. So you apply your entanglement breaking channel or R, and then do the swap test. So that is this pi sim AA prime, which is the symmetric projection onto the symmetric subspace. Then you take the trace, and since we want the maximum acceptance probability, the only variable here that we can maximize over, which is what the prover does, is the maximization over entanglement breaking channels. And then we can bring this, we can show that this maximum acceptance probability is related to the fidelity of separability of a bipartite state. This is given like this, which is just the fidelity of rho maximized over all possible separable states, and fidelity is given like this. It is also known as maximum separable fidelity. So then we show that the maximum acceptance probability is 1 plus the fidelity of separability by 2, and so this is a very neat result. And then so we also so an important thing I need to point out, and which all of you certainly noticed, is that I've not told you how a prover works, because frankly no one knows how to do these optimizations. So we don't have a practical way of finding a prover. So we can approximate this behavior using parameterized quantum circuits. That's one. And also we do note that the swap test is essentially doing like an overlap, and so then we can reduce it to that. We can just reduce it to that, so we can further simplify the circuit. And so but also at the same time, we also note that the maximum separable fidelity can be written like this, as like a maximization over all pure state decompositions of the state of interest, and the convex combination of the fidelity of separability of those the elements in those convex combination. And so we can use this and this result, which is just a modification of this of the prior result, and we get this variational quantum circuit, and which is where we prepare the state and we do a steering measurement. And in the steering measurement, we rotate. So WR of theta is a parameterized circuit whose parameters we can control. And then we apply the standard measurement, which is like computational measurement in the computational basis. And then depending on the state X, so depending on the result X, we apply a unitary on, we apply a unitary u of x on A, and then we measure that, and we accept only if we get the all zeros outcome, which is what we began with. So we've essentially done an overlap test, and so the maximum acceptance probability here is then a maximization over all, is a maximization over theta of the thetas, and I have to read this, sorry, maximization over the thetas. So this is the maximization. So maximization over the parameters of WR of theta is this. It's the maximization of pure state decompositions, and the maximization over theta x is the maximization of overlap, which uses the infinity norm, and which is then the fidelity of separability. So we can also we are going to be running these on current quantum computers, so we need a sort of benchmark, and so we use the fact that fidelity itself is a semidefinite program, but there are no semidefinite constraints available for separable states. So we substitute for those with positive partial transpose conditions and K extendability conditions for both the actual expression of fidelity of separability, and also for our test of separability, we have this expression. We can do the same with PPT channels and K extendable channels to approximate entanglement breaking channels. So this is a plot. This is a simulation of our VQSA, which is for a 3x4, 1x4 classical mixture of two maximally entangled Bell bases. And as you can see, the blue line is our VQSA, and it converges quite nicely to our two benchmarks, all of which agree at 0.93. Again, the jitteriness is because we use SPSA, which is a stochastic gradient descent. So there's a bit of it. And there's also some short noise because we have a mid-circuit measurement. Our mid-circuit measurement here is what makes this possibly a new type of variational quantum algorithm. And we can also characterize our computational complexity using this new class, which is this. And in the interest of running, since I'm running out of time, I'll not go over these. And also so finally we get a test for separability for mixed states, and by replacing the prover with a parameterized circuit, we develop our VQSA, which is a novel quantum variational algorithm, and using the structure of our test for separability, we get computational complexity results that establish a link between steering quantum algorithms and quantum complexity. VQSA can be used to tackle other problems that involve steering, like maximization of pure state decomposition, and techniques may be useful for other entanglement measures that involve optimization of separable states, and VQSA can be used to obtain maximum fidelities for other resource theories. These are my references. Thank you for listening.